with camera. Oh, camera. Oh, yeah, I think it's fine. Do you think I can improve that? Yeah, hello everyone. So today we will take a slight detour and we will look at some load counts. So let me just remind you of what we have already seen. So for L smooth convex functions, we have seen that and for xk minus x star. Then something like after the constants order beta xk minus x0 minus x star square by k. So roughly speaking, we get something like this. Oh, so sorry. So yeah, it looks something like this. Yeah, and then you might want to ask that is this bound tight? And indeed, today we will show that we will show something interesting. I can leave it there. So let me write it together. Okay. Okay, so for any k, which is importantly at most something like n over 1 by 2, what is n any dimension? So here x is in Rn. And any x0 in Rn. There is a function that is L smooth, and in fact this will also be have different derivative is actually quadratic. It's written out to be quadratic. It's like a very nice looking function, such that for any first order method, and that is fine. Okay, so let's just make precise what we mean by first order method. So right now we look at only methods that accumulate gradient information. So we have something like this. So xk should be the span of your initial point, and it should be only linearly accumulating the gradients. We cannot be doing any tricks of taking inverses of matrices and all that. So it should just be only linear combination. Okay, that's fine. Yes, as long as it's only this linear combination. We have something which looks like this. Not exactly, but yeah, something of this type. F star. So F star is the minimum value. And F star is that. This is at least real x0 minus x star square. This looks like this. Okay. And we have some constant. But now instead of k, I have a k plus 1 square. is a bit mysterious. Like here I have a k and here I have a square. But so this is the first thing. So lower bound on how far you will be from the optimum value. And secondly, we also lower bound how far we are in distance of the point. So this thing here should be over it. It's a constant times. So a few remarks on this. So this suggests that either this lower bound is not tight or there is a better algorithm. And this suggests that somehow if you care about how far you are from the optimal point, then you are in big trouble. Because no matter what gain combination you take, you will really have this big difference, right? So you are actually off by a factor of 1/8. Okay. And why is this result interesting? First of all, it kind of tells you where the bottleneck is. This function, like I said, it actually is just a quadratic. So it's possible to just look at it in its full glory and understand what's going on. So it helps us understand, where budgets like this fail. Okay, so hopefully the statement is clear. Okay, great. So now let me give you what the function is. So we will give you a family of functions. So remember that for any k, there is a function, right? So the function you choose can depend on what k you have. And in fact, it can also depend on what x0 you choose. So we can assume that x0 is equal to 0. Why? Because if it is not 0, then I can just shift everything so that it becomes 0. So this is without all the generality. And and now let me define this fkx. By the way, just a warning, even though I'm writing fkx, this fk may not be the fk. They be related, but will not exactly this. So fkx is this quadratic. Okay, so L is this L closeness. And here I have half. One square plus 1 xi square plus minus okay, so this is the function. And okay, this might look a bit complicated because of these summations, but I will draw a picture. I will show this also in matrix form for some small value of n and k, and it will look a bit better there.
So x superscript I is
yeah. So it's the coordinate. So the vector x is
okay.
x1, x2. Good. Okay. So first of all, let's verify that this is actually is. So what do we have to check? I have to make sure that the Hessian has all eigenvalues between 0 and L. Right. So this is what I have to show. By the way, there will be an assignment or more like a tutorial on properties of smooth and convex functions. So if you're not like fully comfortable with things like Hessian and and these notations, you will get used to them. And what does this notation mean? So this just means that give me any direction h. What does this mean? So give me any direction h. Then I will have that. So H transpose gradient square of kx, which will be this line between L and C.
Non-right.
Yeah, this is for any directional way. So for any so let's just verify this. And we also get used to this function by doing that. Okay, so let's compute what this quantity is. So yeah, so simple to I want to find the inner product of Asian times h and h. So what is this quantity? So here we will critically use the fact that this thing is some quadratic. So well, if I have any quadratic in my life, then it looks something like of some x transpose akx. So minus this is okay, it's correct. Okay, it's okay, so FKX looks something like this. And there's an L by 4. Somehow has this structure. So I'm resolving all these square stuff in this AK. Correct. So now if I were to find the Hessian of this quantity of this FKX, what would it be? Who can tell me? Okay, cool. Yeah. Great. Okay, so what's the Hessian matrix? The Hessian matrix is this matrix where the IGF quantity, the IGF term is this. Yeah, so you take your function and you differentiate it with respect to x, xj, and xi. You take the partial derivative, and that's the IGF integral. Okay, so okay, so well, so this becomes a matrix, right? So what matrix will you get if you do this? Yeah, you get L by 4. I say again.
You take asymmetric, otherwise you get AK
Yeah. Yeah, good. So here it will turn out. It's because here you have symmetry, x1 square here, x square here, and yeah. So here will actually be symmetry. So it's not yeah, so you get something like this, right? Yeah, and now I can write down what this should be. So, in fact, if you observe carefully, this will be nothing but L by 4 H transpose yeah. So this is what you get. And yeah, so the point is that this looks very similar to this thing here. Right. So this means that but I already know what this thing is, right? This thing is just this thing. So this is just X transpose. X. So, and this is like obviously non-negative, and therefore this is also obviously non-negative. Non-negative. And yeah, and you can also check by a similar trick that this is also else. Yeah, I won't do that. So, and you can also check that this is at most L times. Yeah, well, yeah, by exactly the same trick. So this is in our function class. So now let's ask ourselves what the gradient of this is and what is the minimum value. Right. So again, if you have a function of this type, then if I were to find its gradient and set it to 0, what would I get? I would get something like okay, what would I get if I were to set a gradient to 0? So what equation do I get? Anybody? It's equal to the first. Yeah. So yeah, EK is equal to E1. So yeah, I get this equation. So let's solve this, and it's a good time to write down what EK is. So okay, so let's see, and now we'll take an example just to make it look a bit better. Let me choose, let's say some n equal to 9 and k equal to 4. K equal to 4. I'm doing this because I wanted k to be at most half of n minus 1, so this is kind of the right thing. So let me write down what this is. So fk. So f4 x. So what is this? This is 4. Square. 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 And finally, x3 minus. Yeah, so that's right. And I get one more term. Yeah, and then there's a next one. Which is not important right now. Okay, so what is AK? So remember, this is how we find the Hessian. This is a good exercise. Let's see. So what is the dimension of this matrix? Remember, X is 9-dimensional. Okay, so this is a 9 by 9 matrix. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6, 9. Yeah. Okay, so let's do this computation. So, okay, so what's the first entry?
2, 1. I mean,
Yeah, so this is 1.
8.
Yeah, 8, so this is 1. And what is the second entry?
It must be two, right?
It's 2.
Yeah.
It's
not two, it's two, yeah.
half outside, so it's half is outside.
Yeah, so 2 the half outside. So it's a 2.
And diagonal entry should be 2.
Yeah, so yes, these are all 2. Good.
Then we
2 until some point, right? Until 4.
Yeah.
There is 0. So this is all 3. In fact, here everything is 0. This is also 0. Okay, so here I have 2's. What do I have here? So what about this side? So
-1 next to the line.
yeah, so here I have -1, and yeah, and also -1 here.
So you want to choose the asymmetric. You can choose the other thing also.
Sorry?
You could have put -2 on the above the diagonal and 0 below, but you want it to be symmetric, so you put -1.
Oh, okay, sure. Oh, okay, great. So yeah, so and these are all 0. Is that it? So you get this kind of tri-diagonal matrix. And I just have to write down what x should be. So if I were to just solve ax equal to b1, what would I get? Okay, so I have this equation. So I have 2x1 minus x2 plus 1. Then I have minus x1 x2 3 0 minus 2 3 4 0. And finally I have minus 3. Yeah. Okay, so I have like 4 equations and 4 variables. And okay, so I will just write down the solution and hope that you can verify it. So the solution turns out to be xi is 1 minus I over a plus 1. So I running for 1 okay. And yeah, and 0 for I'm not okay. Let's just verify. So in this case, what would I have? So sorry. So in the example, x1 is 1 minus 1 over 5. 2 over 5, and so on. Yeah, and so on. Yeah, until x4. Yeah, and yeah, and then you can just check that to satisfy this. Okay, so I want to do that for you. Okay, check it out. Okay, so hopefully this makes you be familiar with this function and AK here. Okay, cool. So well, with this xk in hand, now you also find the optimum value. So fk star is FK of XK. And again, you can do this calculation, and yeah, again, I won't do it here, but this will be L over 8 minus 1 plus 1 over. Okay, so you can just check all this. By the way, this entire exposition is from nested row. So, yeah, I'll just. Right here, so. You can see this calculation a bit detailed there, but right now I'm just using my hands. Okay, so yeah, so now we are armed with our understanding of what the optimum value is and where it is attained. We'll just need one little thing, which is about the norm of xk. Remember that we care about how far our optimum value, optimum point is from the initial point. Initial point, if you remember, is 0. Therefore, you care about the norm of this thing. So let's also do that. So let's calculate the norm. So okay, it is called the bar, it's optimum point. So this is the summation I will from 1 to k, but minus I over k plus 1 square. This is k minus 2 over k plus 1. And I will make some equal to k. So you get k times I, you get that is squared up. And now you can use your high school tricks. So, okay, so let's just, so this is the most ones. And so yeah, from high school stuff, it is k plus 1 by 2. And this is at most k plus 1 cube by 3. Yeah, and then if you simplify this as by 3. So the punchline is that this square of this norm, the optimum point, looks like roughly order k. Okay, so this will be useful later. So I'm just putting this in a box. Okay, so okay, so I think that's enough of this. Okay, and now let's get to the punchline. Okay, so how does all of this help, right? So why is function so useful to give us a lower bound on the distance from the optimum? So here is the key lemma. Okay, so before studying the lemma, let me just put some notation. So let's define Rkn to be the set of vectors in Rn which only have non-zero entries in the first k coordinate. Okay, so all coordinates beyond k are 0. So yeah, that's Rk. Okay, so now here is the lemma, which is the key to everything. So here you can pay attention if you got lost earlier. So again, remember that x0 was 0. And remember, I defined a class of functions, right, indexed by k. And my final function will be one of these functions. So let me call that function p. So we run gradient descent on, okay, not gradient descent, sorry. We optimize. So you want to optimize FP. if P is within between 1 and n. So this is your function of interest. And so K here is the iteration number. So xk is your iterate. And remember that here xk is a linear combination. So it lies in the linear combination of going by our assumption, it lies in the linear combination of gradient of fp at x0 at s1 and the previous curve. Yeah. And let's call this span as LK. Right? Okay. So now here is the key now. So the lemma is that no matter what step size or what linear combination you choose, this entire span LK can never go beyond RK. So LK is a subset of and this kind of suggests why you should get a lower bound, because it's saying that no matter how clever you are with the linear combinations, you can never escape the subspace. And remember that if I want to get to the optimum, I have to kind of get a lot of non-zero coordinates. But in iteration K, I cannot get too many. So remember, I'm optimizing FP. So if I want to get really close to the optimum, I want to get P non-zero coordinates. But this says that look, you can never get more than K non-zero coordinates. So so that's the first line. And okay, so let's prove this now. The proof is actually really simple. So we prove by induction, as you might have already guessed. So well, let's take the base case. So x0 is 0, right? Okay, so and what is the gradient? So gradient of fp at x0. So this is something like I think I erased it, but
It's AKX, it's APX minus.
right. So it'll be something like minus L/4 E1.
Yeah.
So because your square terms will just go away, right? Because it's 0. So only the constant term will matter. That's minus L/4 E1. Yeah, and this, as you can see, is an R1N. So so base case is good. First gradient is in the right of place. Okay, now let's do induction. So suppose induction. Suppose LK is the set of R here. For the less than P. Okay, now now again let's bring back our matrix. Okay, so you can see here that this matrix is tridiagonal, right? So if I take a linear combination of the first k minus 1 columns, then the resulting vector can only have a k non-zero entries. So I'll just write down point. So AK is right diagonal. linear combination. First. Okay, something about am I off by one? Okay, but first. One. No, I think it's fine. No, yeah, because one entry here.
You should say AP, right? Not AP.
Sorry.
The matrix.
Yeah. Sorry.
So AP, so
Yeah.
the matrix is bad.
Yeah, exactly. So the matrix is, yeah, so it's A, B, C, the triangle. The combination of schema on columns can only have a non-zero. Yes, this is like completely obvious. It requires no proof. Okay, so yeah, and that's it. Yeah, so so now this LK, so LK is an RTN, and yeah, and then if you do this combination, is that then the combination of LK and your next gradient tells the XK. This must be the RK plus 1. Okay, so we will just stay this for a minute because this is the place where the magic is. Yeah. Cool. Okay, so I hope this is clear, right? No. Yes. Okay, awesome. Actually, yeah, should probably.
The XK.
Yeah, this is kind of redundant, right?
So the point is that because XK is in LK.
Yeah, exactly. So there is-
When you try and create XK, you can only get.
So I get it. Yeah. So this is redundant. Yes. Okay, so the comment of LK is. Wait, yeah, and FP gradient get XK is okay. I think this is it, right? Yeah. This is all it is.
I think that one, the plot on everything.
Okay. Well. Okay, great. So now, okay, so here is the obvious probability of this. So give me any. uh, 0 to B. So we give me any sequence. with x0 with 0, x0 and xk is in LK. So we must have that fp of xk can never be less than fk star. This is like completely obvious. See why? Because this lies in RKN, right? So, use that one. So, XK lies in RKN.
Oh, okay, yeah.
So, so therefore, the point is that fp of xk is same as fk of xk.
Yeah.
And that is of course and somehow the trick is to make x0 0, because x0 0 makes sure that all your future points lie in the span of the gradients. So your so somehow you can keep adding to this LK every time, and your process behaves like this, right? So initially your LK is just your initial gradient, it's just minus span of minus over even. So initially it's just this, right? And it's that will L1. Right. Yeah. And and since your x0 over 0, your x1 must be in span of minus L over 4 even, and AK times
So yeah, X1 is somewhere in N1.
sorry. X1.
So yeah, X1 is in N1. This should be X2, right?
Oh yeah, it's X2. Yeah, exactly. And the whole trick is that since your AK was diagonal, this thing can only have two non-zero entries. First two. So that's the magic. Yeah, and so each time your non-zero entry will increase by one because of multiplication, and but cannot increase by more than. So this is completely in your head. Okay, now after this is just algebra, but maybe let's just do it. So kind of pretty. So now into the main theorem. And hopefully if I go down, I can find it. Yeah, exactly. Everything aligned right here. Okay, so for any K, I want to construct an F which is L smooth and which has a global properties. So which F do I take? I take an F from this family. I will not necessarily take FK, I will take some bigger thing. So I'll take F2E, F2K plus 1. Okay, so F2K equal to plus. And then let's see what bond we get for this. So now f of xk is at least fk star. And okay, and from calculation which we did earlier, fk star was, I think it was minus L over, yeah, L over 8 minus 1. Yeah. Okay, this is what it was. Yeah, so you this will always be a thesis, whereas your true value is kind of small. So so what is f of xk? Remember, what is, look at this quantity divided by x0 minus x star squared. This is like so I get an L over 8 and I get, yeah, so you get like 1 over k plus 1 2 divided by, okay, the square of this, and remember it is with the non-computation, right? So here this is yeah, so remember x star here is p, right? So that is 1 over. Okay, well, it doesn't really matter what k it is, but the point that this looks something like, yeah, this is the order k. That's what matters. This is 2k plus 1 by 3. So okay, so it's order k, right? That's all that matters. And this is like 1 over k squared. There's some constant times L. Okay, so let's see with this. Okay, so yeah, that's the lower bound. And let's also check the other lower bound. This. Okay, yes, sir. The thing is the other lower bound. Let's do this one now. So xk minus r squared. How much is this? The thing is
how did you go from minus 1 plus 1 by k plus 1 to 1 by k plus 1 minus 1 by 2 k plus 2? There's so you two different, that is the same thing.
yeah, because this is for p and this is for p. P is
Because that's something both of them and you can you get 1 by k plus 1 and 1 by k.
Yeah.
So the denominator came from the norm.
Yeah.
Yeah, denominator is from the number.
Yeah, and that was upper bounded. Oh, because so we had upper bounded at the order k and k.
Yeah. Okay, so now let's try to lower bound how far we are from the optimal point. So notice that at best you can get the first k coordinates matching, right? So this will always be at least. Let's look at the other coordinates. X bar k plus 1 I square. Yeah, why? Because xk is an r here. That's right. So yeah, and now we can just compute this. So remember this is like 1 minus I over 2k plus 2 pi over linear equation solution from earlier. So add a 1 to this. Right. Okay, so oh no, sorry, okay. Here you get the k plus 1 terms. K plus 1 times a 1. It's like 1 over k plus 1. So and twice of 1 over 2 k plus 2 is k plus 1. That's
We can reindex with this one term.
right.
And
Yeah.
you
You
can-
can take it in the reverse.
Yeah, you can do it in the reverse order, that way you don't really want to miss a one.
This time you can do it in the reverse order.
Then let,
So there is like one
j
by,
equals to k plus 2 minus I, and your inside becomes j over 2k plus 2 whole square.
Right.
So, and then you have j from.
this,
From.
Oh, I see. Yeah.
J or whatever,
Yeah.
that way you don't have three terms, you have
Right. Got it.
one, yeah, that's correct.
Got it. Okay. Yeah. Yeah. That's that. Good. Right. Okay. So yeah, that is reindex. That's j equal to 1.
K plus
Uh,
So there is 2k plus 2 minus I. So I, when I goes to k plus 1, they will become k plus 1.
right. Okay. Good. Okay.
And when I goes to k plus 1, j equals to 1. So j equals to 1 to.
Yeah. 1 to exactly. Awesome. Yeah.
And inside is just g over 2k plus 2 square.
Yeah. 0. Yeah. Good. Oh. Okay. So okay, the point is this will turn out to be something like an order case. That's the point. Yeah, it will be like a T. It will be. Oh my God. Yeah.
So you say, yeah, like 1x.
And if you look at what I have to compare against, so x0 minus x star square. Yeah. So again, this number is like it's 1 over 3k plus 1. 2k plus. Yeah. So yeah, if you just do the computation correctly, you will get it.
Yeah, so in this one, the right hand side, x0 minus x star square, that is kind of like integral of x square from 0 to 1. Because you know your xi, when you're doing the sum, the xi is like 1 over I plus 1, right? So 1 over I plus 1,
Oh,
over
okay.
I plus 1, and so on. So this sum is approximately an integral.
Right.
So the right hand side is integral from 0 to 1 of x square. The left hand side is integral of 0 to half of x square. So integral of x square is like is over 3. So integrating from 0 to 1, you get something. Integrating from 0 to half, you get like 1 over 2 cubed. So that's why I get 1.
Okay, cool. Yeah. Good. Okay. Awesome. Yeah, I got something from you. Good. Okay, great. So I think yeah, that completes the proof. So there are 2 points to highlight here. Well, first of all, we got this rate of L over k square, and yeah, so mysteriously this is factor of k off from the upper bound we got, which is L over k. And in the next class, we will see how to improve the upper bound to L over k. That's what accelerated, and it uses something called momentum. And yeah, so we'll see those ideas. And secondly, we have this one annoying thing. This says that no matter what tricks you use, as long as you are using a linear combination, you can never get better than this. This will be addressed today. So it means that you have to go to a more specialized class of functions, and these will turn out to be what are called strongly convex functions. So let's do a quick tour of them. Okay, so what is strongly convex function? Okay, so we say that a function f is mu strongly convex if f of y is at least of x plus the over 2. So notice that if v equal to 0, then it is just convexity. And let me draw a picture to illustrate this. So let's say you have some function like this. Sorry? Oh,
So for L smooth function, we had C was.
you get the other way around. So you say that
That was upper bounded.
yes, the thing that okay, here is the point. X and here is some point y. So it says that there is some quadratic here. So okay, so the first complexity says that if I draw this tangent, then f of y is at least f of x plus the linear approximation. So this is the linear. And this way, that even higher. Okay, so yeah, there is actually a quadratic which gives you this additional term. So yeah, so there is this quadratic inverse. Okay, so this is quadratic lower angle. Smoothness, if you recall, was a quadratic upper angle. Just to be the smoothness and this is trigonometry. Okay, great. So yeah, so that's trigonometry. And here is let's just give an alternate definition. Yeah, these are useful things to know. So f is strongly convex if and only if f of x minus mu x square equal to convex. So that's one definition. Okay, one alternate definition. Yeah. And another alternate definition is of if and only if x y minus y fixed here. And this might again remind you of smoothness, because there you get the same thing in the other direction. So, okay, so we have two alternate definitions of trigonometry. And okay, so now let's see what trigonometry has. Here is the main pair dimension. So if f is mu strongly convex and s, so if you have both of these things, then if you run gradient descent with step size at most 2 over mu plus l, then you have that xk minus square is at most 1 minus 2 mu L over plus L times h. Because k 0 minus k. This is very nice. Okay, and this is really nice, right? Because earlier you were suffering from this 1/8, yeah, and now you have this really nice exponential decay. Yeah. And yeah, and then if I choose x to be 2 over b plus n, or b plus n, this quantity becomes at most. Okay, so let me define the condition number. So condition number of the function is defined as n over b. And it is more than 1 or less than 1?
Greater than.
Huh?
Greater than.
Yeah, okay, so okay, so this is at most condition number of f minus 1 plus 1. Yeah, so this is what first exercise. So you get this, it is plug here and check this. And yeah, okay, so this is the main thing, and you can also get a bound on the function value, which I will not write. Yeah, you get similar bound on function value. Similar decay. Okay, so let's try to prove this. Okay, so here's proof. So let's again look at this RK, which was xk minus x star. Okay, and as in the previous case of smooth functions, let's look at RK plus 1 square. And let's try to, that's what you care about, right? You want to understand how this decays with time. So you want to compare RK plus 1 square with what's RK square. So let's now change it. What is this? This is xk minus h gradient fxk. That's the area difference there. Minus x star. Okay, so now let me combine this with this, and I get RK square. I get minus 2h inner product of gradient. xk minus x star plus h square times the gradient. Okay. Okay, so really you have to understand this quantity. And similar to what was the case in both functions, you have to understand the quantity of this type. And so you have to like prove a theorem about this. So let's do that. There is a lemma theorem. So it says that for any mu strongly convex and L smooth function, you have that gradient of f at x minus gradient of f at y. Least mu L p plus L square plus L. And why will this be useful? So, well, we will plug x equal to xk and y equal to x dot here. And well, we get gradient of f at xk straight away. What is gradient of f at x dot? It's 0, right? Yeah, so that goes up. So we get exactly this thing. So we say that okay, this airport is going to be sufficiently large, and since you have minus sign here, it will decrease this quantity. And hopefully that will counteract this h square. F square. Okay, so let's prove this lemma first. Okay, so I won't prove the whole thing, but I'll give you the idea of the proof. So, idea of proof. So again, similar to the proof which we did yesterday by building a function p. So yeah, it's kind of similar. So I'll just give you the idea. So idea is to build this function p, which is f of x minus 1 over mu squared. Why is this useful to do? Because recall that one definition of non-complexity was that f is strongly convex if and only if this function is convex. Okay, so now I can kind of forget about non-complexity. Now I'm in a familiar world of complexity. And so the real convex. And gradient of p at x. So what is that? Well, that is the gradient of fx minus mu x. And now, crucially, this is convex, and it is also L minus mu. Okay, so let's see why. So okay, let me just give you a quick proof for twice differentiable functions. So remember that a smoothness means that your Hessian is at most L times the identity matrix under this PSD inequality. Under this PSD order. And so there's smoothness, and there's also at least mu times the identity under PSD ordering, and this is tropometric. This is smoothness, and this is mu tropometric. Yeah, so these are the equivalent conditions. And now you kind of see that take out this, because the plan was half mu x square, then I get that this is that. Okay. So f minus half mu x square. This will be PSD ordering most L minus. Okay, so that's like an immediate way to say this for twice differentiable functions. And by the way, so as you can see, the PHP ordering is kind of very useful to use. So let's go to check this later, what this means, and maybe I'll just define it quickly for now. So this just means, so PHP order at most B just means that B minus A is PSD. So which means that X transpose PX is always manipulation. Or in other words, it means that all the eigenvalues of this gradient square are sandwiched between L and B. So subtract out a mu, then will be between 0 and L. So that's a picture. And again, so I think we've made some tutorial to have you internalize these rotations because they are like very useful. Okay, great. So this is L minus mu smooth. And now you can use all your tricks from smooth convex functions, which we have already learned, and maybe also remember. So already we have seen this trick that okay, for a smooth convex function, you have that y at least because it's L minus mu smooth. Yeah. So this right here is a property of smooth convex functions, and and now if you just plug P back in this, this definition of P into this equation, then you manipulate this, you just get this. Okay, so again, I won't write out, but this is just the idea. Okay, great. Okay. Also, a small trick here. So here I assume that L is strictly more than mu, otherwise this is 0. So if L is equal to mu, then actually everything simplifies because then your lower bound and upper bound are actually tight. So then this, great. I think it's exactly mu or L times IM, and then everything is simple. Okay, yeah. So I'm not giving the full calculation, but you can just work it out from here. Okay, so now with this key lemma, I can now get back and analyze my essay tool. So remember, RJ plus 1 square is RJ square minus WH. Okay, so again, let's use that, and here I will get mu L over u plus L xk minus x0. Sorry, x star square. Remember, I am plugging x equal to xk and y equal to x star plus 1 over plus L but xk. Yeah, because gradient is 0 at x star square. Okay, great. And and now it's looking nice because this thing here will hopefully help out here. So there's RK square minus BH. And okay, this is again RK square. Here I get 8 times 2 over v plus L plus H. And now, as long as it is not too large, which is at most 2 over v plus L, this is always this is equal to 0. And so this is the only time which matters, and yeah, then you get what you wanted. Yeah, so that will give you the sequential decay from the top equation. Okay, hopefully that is useful. Any questions on this? I think it's a bit heavy class.
So this is this QF minus 1 over Q plus 1. It shouldn't be square, like it should be 2K. Like if you substitute H equals to 2 over v plus L.
Right.
2 minus L squared over v plus L whole square. So that's QF minus 1 over Q plus 1 whole square.
Okay. We did understand 2.
And it should be 2K. The top one is
Yeah, I see.
second one should be.
Okay, second and good, of course, yeah. Yeah, good catch. It's too great. This is- Yeah. So. Yeah, good. Also, side remark. So, one could also ask for a lower bound for strongly conversations. And it turns out that you get a lower bound like this, but instead of QF, you get square root of it. So, and again, it turns out that you can get a better algorithm and get a square root of QF here. And yeah, again, using ideas similar to what I was discussing in the class. Okay, any more questions on today?
So the load bound was proven by collecting a set of functions which are upper bounded by the dimension which are given. So,
Set of functions. Okay. So if we will begin dimension n
yeah,
and and your
seems like a bit unusual, right? Like you cannot allow the number of iterations to be beyond the dimension.
good, very good point. Okay, so he's saying that in fact, if you remember this statement of the lemma of the theorem, it says that your number of iterations should most something like half of yeah. So indeed, true. But it still kind of gives you some handle on the initial phase of the algorithm.
It makes sense because the
Otherwise, not.
should be.
Yeah.
So your lower one also has to be. So the number of iterations that the gradient is carrying this dimension, it does not depend.
Yeah, exactly. Yeah,
So,
true. Something.
it is, so, yeah. So it's like it's a high dimensional optimization because
And here, if you actually allow K to go beyond that, then you can actually reach the bound. There's a different pattern of algorithms.
Yeah, because here we are saying that no matter what the dimension, we want a uniform.
Yeah, exactly.
So in that case, you're letting the adversary choose a dimension also.
True.
Yeah, so that way you can just choose a dimension to be twice of K.
But yeah, this will another part. Okay, great. Yeah, if you have no further questions, continue next time. By the way, this inequality you did last time, right? And this inequality you did last time, right? Not this one. You did like another variation.
Yeah, not with this, maybe something like this, but it's like,
Yeah.
no, actually, yeah, but without the L in between. Right? Yeah, no, actually, I did it without the.
Yeah, put it. You just trading here.
Yeah.
The grade with just the L, right?
No?
We did with just the L, one of
Yeah,
our
yeah. Basically, kind of the right in the.
Yeah. Right.
Screen.
Oh, yeah, thanks.